Today I would like to talk about the winner binary in the era of IoT, the potential of the winner binary analysis. These are the works of the students, and I have been working on it also for years. So let's take a look on the brief history of computing since 1980s. We are going to talk about the mainframe. So in the 80s, we know the PC was invented in 81, and then there's as those years, the PC are collected through the internet, and later, right, when we move to the era of Wi-Fi, 3G, 4G, we know mobile devices are also connected to the internet, and in the last decade, we see many IoT devices, right? They are connected to the internet. In the last few years or so, the edge computings, right? Now you see devices like drones, the cars, phones, or computers, right? They all connect to the internet. And here are some statistics about the number of IoT devices are connected to the internet. I cannot say the exact statistics there. So like billions, right? So billions of devices connected to the internet. And here just highlights a number of security incidents in the space like IoT. I'm sure everybody heard like earlier Stuxnet and later those automotive hacks. So in terms of, right, we are binary analysis people, right? When we in the era of IoT, there are actually tons of opportunities. So these are things I want to share with you. So maybe let's first look at how does IoT ecosystem looks like. Take our IoT devices as an example. So typically IoT devices have our like a physical device, and then there are apps in the phone and talk to the device, and then device will also talk to the cloud, right? There are typical three parties there. And if you look at the device has our stack architecture. Right, so on the top there are like applications, right? People build various applications on top of like the middleware and the operating system and hardware. So applications like smart lights, Fitbits, or thermometers, right? So those are those various IoT gadgets, devices, and in terms of middleware, things like Amazon Cloud, right? Those like Qt, MQTT, all those middlewares, they provide SDKs, APIs for IoT developers to easily build their applications. And then there are OSs like RTOS. In terms of hardware, we see these ARM processors, Intel processors, right? And there are other chip manufacturers like Lodec and Texas Instrument, and the processors, the RAM, storage, I/O. Usually they are integrated in the board. So this is, you see from, if you open a device, this is what you will see there, right? The talk today is about domain-aware binary analysis. So we know binary analysis is challenging, and when you were giving a binary, you have to say recover console flow and understand the meaning of the code, right? We are security people. Oftentimes we say, hey, let's find vulnerabilities in the binary, and meanwhile try to understand the root causes of the vulnerabilities, right? Domain aware. So actually, why we need to domain aware binary analysis here, right? Well, one reason is one size does not fit all. Particularly in the IoT space, right? There are heterogeneous architectures, right? Different vendors give different APIs. So and now your universal binary analysis may not work. Say, can I have an algorithm to discover vulnerabilities in Bluetooth or in the robots, right? That's different. So you need domain specific insights to solve this problem. And also interestingly, domain insights, the domain knowledge can also help binary analysis. This is also since I will share you our experience. when you dig into more on this particular domain, and you can leverage those insights to help binary analysis, and then meanwhile you can transition to other domains. So in the past few years, my students and I have been working in this space. We have published a number of works here. For example, the ones we recently, maybe last year, we look at the infotainment system of the Tesla, that huge screen, and many apps actually are built on top of the Qt framework. So then we take a first look on what's the challenges when you look at the Qt binary, do reverse engineering there. So we have upcoming papers in the using security. And last year at CCS, we look at, hey, let's look at the apps. I talk about IoT, you have our app components. So we go to Google Play Store, let's look at all those IoT apps, then they understand, hey, what are those challenges, security issues with in that space. And then also interestingly, right, we look at the games. So the games, particularly those unit games, right? The game providers give you SDK, and developers can easily build game apps. And those engines actually they are binaries, not a Java code. It's actually little binaries. So the particular domain we look at is like payment. So how the payment API gets implemented, and are you able to detect payment flows from the binary code? So that's actually the paper we published last year. And we also look at largest applications. Look at the board, the firmware. So we found something interesting there. Like there are peripheral registers have some hidden mappings. When you directly look at the binary code, you may not be able to you may encounter like data code. But in fact, they're not data code. There are some kind of hidden mappings. So and we did a study there. And 3 years ago or 4 years ago, right, we look at the Bluetooth firmware and look at the vulnerabilities. Like in the Bluetooth link layer, there are misconfigurations, and we developed some algorithm there to uncover those link layer vulnerabilities. And also lastly, we look at the vehicle dongles and how they collect to the car and what are other security issues. So those are all, you can see in this IoT umbrella, right? We do this all these are binary analysis. So today I would like to share maybe 3 pieces of this work, and to hopefully to inspire you. There are lots of opportunities in those IoT space. Okay, so let's first look at our Qt reverse engineering work. So Qt is our C++ extension. So you can imagine the later binary becomes compiled from C++. Qt has been widely used to build like GUI application, networking applications, database applications, and multimedia applications. Been widely used in this space. For example, like the Photoshop, actually, there are Qt components, and even your virtual machine monitors, right? And they have this Qt components there. BlackBerry, like also the operating system, like BlackBerry and WebOS, Qt is being used, and actually many industries, right? For example, automotive industry, Mercedes, Tesla, they use Qt to build applications. So maybe let's take a look on the Tesla infotainment system. So Tesla infotainment system, so that huge screen, right? Typically user interact with that front end, and front end has our CID called Central Information Display, that huge screen. And IC stands for Instrument Cluster. Basically, you can see your speeds, your RPM, and the CID gives you various applications, right? You can play music, navigation, and so on. And the instruments show you, like I said, speeds, your RPM, and then this is front end. The back end will talk to the cloud, right, through the VPN, and there are modules like cellular network module or Wi-Fi module, right? They collect to the cloud, and internally there are like Ethernet switch and gateway and CAN bus. This is at a very high level the infotainment systems, how they are collected. So here we are interested in binary analysis. So we noticed there are tons of cute binaries. Okay, then we wonder, hey, how are we going to analyze these cute binaries? Can we use the existing techniques directly, right? Can we apply them and analyze those? Okay, so again, reverse engineering, is the key steps to understand and to vet whether there's vulnerabilities in the binary. And yes, you can apply, right? You can apply existing techniques. In general, we know for binary analysis, we have typical challenges like, hey, how can you recover the control flow graph, right? But however, the Qt, you can imagine, is GUI rich programs. In these programs, there are tons of callbacks, right? Then, hey, can you directly apply existing techniques to recover the control flow graph? Okay, it turns out it's challenging. You cannot directly apply. There are some, you have to, solve this problem. Like, hey, how are we going to handle indoor control flow, like especially callback indoor calls? And meanwhile, symbols, right? When we do RE, we know, hey, if I know the name of the function, I have better understanding of the semantics, right? Or variable names, right? So those are very helpful for you to do the RE. So here, typically, the code striped all those symbols, right? Then is it possible to recover symbols to help you understand the binary, right? Those are, the challenges. Interestingly, when you look at the Qt binaries, also the Qt internals, right? Qt actually is a framework, it's a C++ extension. There's something very interesting. For example, Qt provide a signal and snout. So what is signal and snout, right? Essentially, it's a mechanism to collect the callback functions. Okay, it's well specified, well defined. Then you can use that, right, to recover callbacks, indirect calls. Okay, right. So originally the signal and snout was designed for efficient callback implementations, and we can actually use it, leverage it to identify those Qt specific callbacks. If you can collect all those callbacks, you get a control flow graph, right? You can traverse control flow graph to identify critical components, to many other things. The second interesting mechanism is the dynamic introspection. So Qt provide this mechanism, introspection mechanism, is for the code to at runtime retrieve the let's say the members in the class and then update the states of the class. So and then actually we can repurpose this, right, to recover the symbol. So so those two unique insights, right? When we dig into more on those Qt binaries, we find, hey, there are unique mechanisms. Why don't we leverage this, right, to help our binary analysis? So let me use the example to illustrate those mechanisms. So the signal and the snout. Here I show you a very simple program, code snippet, and you can see there is our dialog and the edit box and OK button, and this GUI, there are two callbacks. Callbacks are using those collect APIs, provided by the Qt. You can see the text change is a signal and updated text is a snout. So updated text is actually it's a function. So when user enter any text in that edit box, the event text change will be invoked. And then when text change is invoked, basically that function update text gets called, right? You can see update text will set the edit box with the content, right? Providing that parameter. So that is basically that is the callback mechanism, right? You can leverage those signal and style to collect those, callbacks. And the second, mechanism in the Qt is the dynamic introspection. So what does this mean? So here is another example. So you can see there's the OK button, right? OK button, when user click OK, then it will trigger editing finished event, okay? Inside editing finished event, so basically, so for this program, if user enter text like a secret, it's a proof of concept program. If user enter text as secret, we're going to change that secret to something else. Okay, so basically at line 24, we say, hey, if the value, if user provides secret, value is secret, let's change it to the test. So how we do that? And in line 26 is about set property, right? You can see, hey, set property, the window.text with string tests. So we're going to change the secret to test. And how we do that? So basically, inside Qt, there are some metadata, okay, property table and string table. So I show you the index for them. Actually, for this particular example, is index is 0, and you can query that table to know the type of the string, and also the symbol table tell you the name is test. So in this way, right, you can see because of this unique metadata, it reveals you the symbol name, okay. And then you can continue the execution, and eventually you can see here we set up the window.text with test. So you dynamically change the content in the display. That is called dynamic introspection. Okay, so then fundamentally this metadata cannot be stripped out, otherwise it wouldn't work. Then you can leverage this, right, to recover symbol names to help reverse engineering. This is exactly what we did. The details are in the papers. I'm not going to share how we build that, but here I'm just going to tell you the evaluation. So we built a tool called Qt-IE, and we use it to analyze those Qt binaries in Tesla infotainment. One application here we focus on to uncover those Easter eggs, because Tesla is known to have several Easter eggs, right? And our question is, hey, are there any other hidden things? Why user can enter some kind of particular words and trigger something interesting, right? Sounds like cool. And are there any like backdoors, or are there any like hidden commands? This type of issue, right? So we'll say, hey, is there any issue there, right? So can we analyze the code? And also we see there are news report about the Easter eggs. Are they complete? Can we find all of those Easter eggs? Right, so those are the simple questions we asked, and to identify, let's say, Easter eggs, you can use fuzzen, right, to do dynamic analysis, or you can say, hey, let's look at the input. Let's look at how the input gets compared, right, in the binary code, and maybe from there we can imagine the user enters some, let's say, Easter eggs, then there was some comparison, right? So we can look at those comparisons and to identify all those Easter eggs. So basically focus on inputs, right? How the input gets validated in the binary. And some results. So basically we just focus on the input validation logic in the Qt binaries and identify the user input variables. Again, we can recover symbol names. So here I show in the table, right? We know the symbol names. For example, like a password text field, right? We see this, and this gives us lots of hints. You don't have to look at all this code, right? You can focus on some particular code snippet. And also once we have the symbol names and we identify the user input variables, and also because we recover the control flow by using those signal and snout, right? And we can traverse the control flow graph to say, hey, how the input gets processed from there to identify the Easter eggs. So here are the results, and we identified 7 Easter eggs, and as I show screen on the right, if you enter Mars, and then you will show a map in your central display, and we confirm all of this actually in our central information display, and also interestingly, not just Easter eggs, we also identify some other things like access tokens. So those are basically some mission critical checks. Okay. So for example, if you say I want to enable diagnostic mode, so you can diagnose your Tesla vehicle, or you can have some kind of development, do some patching, updating, right? Those are dangerous. Okay. So the first two secret tokens are vehicle specific. However, also interestingly, we also identify some kind of like a logic, right? Some token got some CRC and equals that hex number. And my students actually develop a very simple Python program, spend 30 minutes to calculate that token, gets that type of value, and enters that value, can make Tesla vehicle becomes this develop mode. And here I also show you the screen on the right? That's how when you trigger this mode, what you can see there. Lastly, we also find some like a master password. So how we find this, right? Again, we look at this input validation, like how the input gets compared and so on. So there's a one like 3500. So this is for you to exit valet, right? You go to the hotel and pass your vehicle to the in, right? You put the valet mode, and the guy cannot drive far away, right? But the guy can enter those like this to exit the valet mode. Okay. So we report this to Tesla, and actually they have eliminated, right? They acknowledged us, and they eliminated the feasible path to trigger those. So add more access control and make it harder for normal users to trigger those. So this is what I talk about, right? So basically, give you a heads up. The paper will be presented in the August using security, and we basically develop our Qt RE to analyze the Qt binaries by leveraging domain insights, and the code we will make the open source. Okay. All right. So this is about by looking at particularly the C++ extension, right? The Qt framework, and you can actually leverage this domain insights to analyze binaries. Next, I'm going to talk about the Bluetooth firmware analysis. We know Bluetooth today is ubiquitous, right? All your phones has Bluetooth enabled, and so many IoT devices, right, collect through Bluetooth, and there are, and then we may wonder, hey, why is so many Bluetooth devices? Why is that, right? Well, the reason is actually there's a very low technical barrier. You guys can actually develop something like this. Okay, just purchase our boards and write some apps and manufacture it. Okay, so for example, right, on the CPU chip side, there are like Logitech and Texas Instruments, right? They provide those boards and CPUs, and then Android framework, they give you those SDK APIs, right? Even cloud have those like IoT hubs. So it's so easy actually to develop those IoT devices. And that's why, right, today so many those IoT gadgets, IoT devices are there. But our question is, we look at the Bluetooth ones, we wonder, hey, are they secure, right? If you look at security of those from network security perspective, because Bluetooth is a communication, then communication, it means the packet exchange, and you wonder, hey, are there any, say, can you do man in the middle, right? All those type of things. Okay. So show you the Bluetooth link layer vulnerabilities. What are those vulnerabilities you can think about, right? So for the Bluetooth devices, usually there's a peripheral, there's a central, right? Central is your phone. Okay. When the phone talks to your peripheral, let's say your smartwatch, right? So your peripheral will first broadcast. Say, hey, I'm here, right? Broadcast a message. When you broadcast the message, there could be some vulnerabilities like, hey, will you change your identity? Because if you never change your identity, people can track you, right? Peripheral always broadcast a constant identity. Yes, you can track you. So you must configure the device to have a randomized MAC address, right? So first of all, there could be subject to identity tracking, and then at communication layer. If you configure your device with like just works parent, that means you're subject to active man in the middle. So active man in the middle, the guys can actually intercept your traffic and modify it. And also, if you support legacy communications, then you may subject to passive man in the middle. So basically, this is domain knowledge, right? Say, hey, how do I know there's this type of vulnerabilities? They're no longer buffer flow. Okay, here we're looking at those configuration, misconfigurations. Then our question here is, hey, how can we identify those? I have a firmware, right? Can I identify this? Well, you could look at traffic, or you could look at the mobile apps. And here we say, hey, let's look at firmware, because fundamentally, right, the code will be executed, and let's look at the code. And here is an example on what are domain insights, right, domain knowledge to identify such vulnerabilities. So here is a code snippet of a real-world firmware code, and this firmware use JustWorks parent. And now the challenge for us is, hey guys, can you identify this firmware just use JustWorks parent? Can you do that, right? So you can execute the code. So basically, you can see at 9.1 it moves a value, right, to register and R2, and then 9.5 is do some kind of data bit logic, and then at 9.6, right? At 9.6, it's going to access our particular data structure, okay? And this data structure basically encode the parent features. The parent basically, the parent will tells you, hey, will you use JustWorks parent or some other parent, right? So in this particular example, the value is actually 0xd because we calculate, right? On scroll on the right, there's our register value, right? We do the calculation. R2 register is 0xd, and then here, what does 0xd mean? Well, and here, and also yes, and also at line 10 there will be our a call interrupt. Basically, SVC is an interrupt. It will call the function 7f. That 7f is actually well defined. It is basically set parameters reply. So basically, that is a particular SDK function. And when people call that functions with the corresponding parameters, you know the meaning. So here, a particular example like 0xd. 0xd, you can see the encoding, right? The first one is the BOND, basically says whether you have to pair or not. And second one is MTM. For the MTM, you can see the value is actually 0. What does that mean? That means this guy is subject to actually, is not defeating man-in-the-middle. So basically, it's vulnerable to man-in-the-middle attack. So now you can see, for this example, guys, let's identify this vulnerability. How are you going to do that? Well, you have to reason the code, right? Calculate the values and require domain knowledge about these particular APIs and particular values, right? If you're able to do that, you can identify tons of. I give you all this framework. You can identify whether they are subject to, let's say, insecure parent, right? This is how we do that. So of course you have to identify the correctly disassemble the binary code, figure out the data structures, and resolve the values, right? Those are some other challenges you have to do this. But the key point I would make here is figure out the domain. Use the domain knowledge, domain insights here, right? Like SDK APIs, the values, all of that. You can do this, okay? I'm also going to talk about the evaluations. I'm not going to talk about the technical detail. You can refer our papers. So for this work, we basically first we had to get a firmware, right? So how you get firmware? Wow, interestingly, you can Google Play has all those apps, right? Those apps actually contains firmware. You wonder, hey, why is that? Why people put firmware code in the apps? Well, maybe people just lazy. They want to do the upgrade. They put the firmware code in the apps. Okay, when the device is going to talk to the apps will say, hey, I have a new firmware. Maybe you want to upgrade. Then you directly use the app to upgrade the firmware. Now we can actually directly unpack the apps to get all the firmware, right? So we got a lot of actually Bluetooth firmware by using this approach. So, for example, among the Google Play's App Store, 2 million free apps, we got like 13,000 BLE apps, and we unpack it, and we found like about 800 firmware, and most of them are low-tech firmware, and some are TI firmware. So we got firmware for free, right? Now we have the firmware. Let's analyze the binary to uncover vulnerabilities. And here are the vulnerabilities we identify, right? So for example, whether the device subject to identity tracking. So basically, did they configure randomize their MAC address? If they never do that, that's vulnerable, right? We found, wow, most of them, they just configure static, they don't change the MAC address, okay? So those are the devices in that category. And also I found about 70% of them just use JustWorks parent. So maybe they don't care security, they just JustWorks parent. bad guys can do those active man in the middle. So those are the devices we identify, and also hormonal then subject to like passive man in the middle, right? These are basically this support legacy parent and they're vulnerable to those. Okay, so anyway, so this is we use domain knowledge, right, to build our static analysis tool to find the configuration vulnerabilities in the Bluetooth devices, and the tool is open source, and I welcome you to play with those. Okay, so the last piece of work I would like to talk about is looking at those boards, look at those peripherals. Okay, so particularly look at the microcontrol units. Okay, the MCU, right? So the MCUs are the chips inside those board, and they're ubiquitous. Okay, drones or your smart light bulbs all have those MCU, and remember we have those 700 firmwares, right? We want to analyze that actually. So maybe let me first talk about those MCUs. Okay, so for the MCUs, you can see MCU firmware. You already talk to peripherals, right? The peripherals like those modules, like Bluetooth, Wi-Fi, or speakers, right? Peripherals are inside the provided board usually, and firmware control the peripheral, right, through the peripheral registers. Okay, and peripheral executes firmware through the corresponding interrupt. This is what at very high level for these microcontroller units. So in terms of vulnerabilities, you could still go find memory corruptions, right? And also there may be privacy leakage, maybe some peripheral malfunctioning. To analyze the firmware, you could use approaches like hardware in the loop, basically test the firmware by using corresponding hardware together to test this, right, to dynamic analysis, or you do rehosting, right, emulate firmware without using hardware. I mean, in the past few years, numerous papers published in the rehosting, right. So however, there's one common challenge, that is how you model peripheral processing. Okay, that's a common challenge. Let me use an example. Okay, this is a great example to illustrate what's going on there, why you cannot directly look at the code. So here's a very simple program, and let's execute the code. Okay, at line 1, it basically set the red clock. Set the red clock as an address, right? That is a peripheral address, like 400238800. Okay, and line 2 is, you can see, set the value, right? Set the value as that 0x1000 to that red clock. Okay, and then basically set the 24 speeds. And then line 3 is check, right? Check that value, whether, and with 0x200, right? Where is 0, right? Check that. You say, hey, this code doesn't make sense. That's a dead code. Because line 2, I set that value, while line 3 is do that comparison, right? Check that, test that beats, okay? So you can see, we already, you can see in the bottom, we see red clock at that address, right? The value is 0x100, but line 3 is testing, hey, is that 25 speeds get set, right? Obviously, if you use directly emulate the code, it doesn't make sense at all. And that's a dead code, right? It turns out, this one will evaluate to this one, right? Because it doesn't satisfy if you directly look at the code. However, if you look at the real execution, okay, the real execution on MCU hardware, if you set at line 2, if you set the value red clock with 0x1000, right? Screen the button, you can see the value actually becomes 300. Okay, so hey, why is that? Is that possible, right? So in the real execution, line 7, the value of line 7 will be returned. So my students spend half year debugging this. So initially, we got the 700 firmware, right? Let's throw into the CoEMU. Let's throw in this emulator to analyze that. And we say, hey, this code doesn't make sense. And we run in the real, because we also purchased the Lodec development boards. We run in the development boards. You say, hey, what's going on there? It doesn't make sense. So then we spent, many hours there to understand why is that. It turns out there is a hidden memory mapping. So, so what is this, right? What is hidden memory mapping? So the peripheral register bits, in fact, right, they get simultaneously updated, okay, by the MCU hardware, because some bits are semantically relevant, okay? So for example, like if you set 24 bits, the 25th bits actually automatically set by the hardware, okay? If you stare at the code, doesn't make sense. Only when you look at the real hardware, it turns out, yeah, that is how it works. So like I show you here, right? At line 2, you set that value. Actually, it automatically sets 25th bits to 1. This happens in the hardware devices. Okay, direct look at firmware code. Don't say that. You need the device in the loop. So what is this? Right? Why people doing this? Right? Well, it turns out it's called autonomous peripheral operation. Because maybe we are a lot of EE people. We don't know this knowledge. We just direct previous firmware. We figure out something's wrong, and we spend numerous hours to eventually find, oh, that is the reason. Okay, and it's a hardware feature. Okay, in the microcontroller architectures, and the peripheral performs its operation without CPU intervention. This is to save energy. Now it's we look at the manuals and we realize, oh, that is the reason. For example, here's the manual also talk about that. So when 24 bits, right, get set, actually they also set the 25th bits. So basically, you look at the manual, you can find this out. Now the question for us is, hey guys, can you automatically discover all those hidden mappings? Well, you say, hey, let's look at the manuals. Well, that's tedious, so tedious, right? So so here the question for us is, can we design a system to automatically reveal all those hidden memory mappings, right? Yeah, so we basically built such our tool, okay? So, of course, there are also challenges, right? For example, how can you identify all those memory writes? Remember in my example, right, at line 2, we have to set that value. We have to do a memory writes, write to that value, right? Write a value there and observe what other bits gets updated, right? So now here is, hey, how can you enumerate all those possible memory writes to peripheral registers, right? How can you do that? And meanwhile, hey, how can you identify those mappings, right? You do a memory writes there, observe what of those bits gets changed, right? You do all of those operations. And meanwhile, maybe there are some dependencies, right? So there are tons of challenges if you want to do that. And of course, this must be dynamic analysis. You cannot static look at this, right? You must do dynamic analysis. So yeah, we have a solution there, which is to this on-demand, right, memory mapping and do the differential analysis. Basically, you can imagine, take a snapshot before memory writes, after memory writes, and observe what are the bits gets modified and summarize that, right? So and also you have to prepare those memory contexts to as the right context to do the right memory writes. So those are some challenges. So if you're interested, I encourage you to read our papers. And we built a prototype and we tested with a number of MCUs. Like a Logic MCU and STM electronics, different versions of that. So we evaluated with 50 firmware, and 41 of them from Logic, and directly their SDKs, they provide this firmware, and also the Mu paper, they evaluated with those 9 firmwares. So we got those from the authors, and we tested them, right? So hey, how effective our tool is in terms of revealing those memory mappings and why it's important to reveal them, right? So yeah. So here show you the result, and we basically again do dynamic analysis and we run it, and we monitor all those memory writes to the peripheral registers. So here I show you some results with those, and for example, for the first firmware BK free RTOS, right, we observed there are 21 writes that cause memory mapping operations, and so basically there are 22 memory writes can reveal hidden memory. There are the hidden memories mappings in these 22 writes, 21 writes, memory writes, and also one memory writes can actually cause up to like 7 different locations there gets changed. So basically, one memory write can cause 7 differences in the memory. So here we show some interesting statistics there. So right, and we integrate, right? We build this. Initially, we say, hey, we have those 700 firmware. Can we do the fuzzing, right? Can we find vulnerabilities? Okay. Then we have to say, oh, let's integrate with an emulator, right? Because mu sounds like a state of the art at that time. So we say, hey, let's plug in AutoMap result with mu, right? Because AutoMap, basically the tool we call AutoMap, basically tell you this hidden memory mappings, like, hey, this bit is mapped to that bit. If this bit has a value like this, the other bits must get updated simultaneously, right? To give you the consistent semantics. And here I show you, right? So we build a plugin to mu. Basically, when mu is going to access a memory, if that memory is a peripheral registers, because we have the knowledge, right? The hidden memory mapping, we will update that, right? So here we integrate that. You can see the results, right? With our tool, with our tool's help, mu is able to exercise more basic blocks. Okay, like one of them, the gateway framework, we make mu exercise like up to 16% of the more basic block. You may wonder, hey, why is that? Remember, mu only look at the framework code. They look at framework code, they think that code doesn't make sense. They will never execute that code because remember my line 3, right? That's data code for it. Right, it wouldn't execute those. But we tell them, hey guys, though, and if some register has some other values, you can imagine, other code you should exercise as well. So basically, we help those, and we didn't find any memory crash type of vulnerabilities. That's why we cannot publish in the tier 1 conferences. So this paper is published in the RAID conference last year. So my student actually spent 2 years on this. Okay, so what is this, right? This basically to say, hey, well, if you analyze those framework code, sometimes you encounter some errors or some kind of challenges there. When you dig into more, you can find, oh, there's some kind of interesting URI findings, and you can develop some algorithms to automate those findings, right? This is basically the work AutoMap is about. And also, again, we released our code. If you're interested, I encourage you to play with. What I talk about today, right? So I share with you guys, in the era of IoT, heterogeneous architectures, numerous different frameworks, different architectures, different SDK, different APIs, tons of differences there, right? And here, there's a need to use domain knowledge, right? For example, like this, the framework example I talk about, the peripheral example I talk about, right? You don't say that in the x86, right? Because we directly look at the code and everything makes sense. When we put that in the framework space, doesn't make sense at all, right? You have to resolve those, use domain knowledge to resolve some issues there. And here I talk about different mechanisms can be used. For example, you can see when we look at the Qt binaries, right? The Qt binary has those signal and snouts and also dynamic introspection mechanisms, right? You can actually leverage that. It help us, right? So and new techniques for binary analysis. Okay, so right. So like I said here, we should really encourage those efforts because as long as you can justify these domains are valuable. For example, here we talk about Qt. Why you guys look at a Qt binary? Why you don't look at other things, right? In fact, right, in terms of, this is the statistics we got from the GitHub repo. So basically you can see, just look at C++ frameworks, right? Qt, of course, Qt is ranked number 1, okay? Like 45,000 repos actually they are Qt. Number 2 is actually iOS, right? Robotics. Guys, I'm sure there are lots of issues with those. If you are very interested in binary analysis, I'm sure you can find many interesting problems, right? For example, in the iOS ROS framework or, Boost framework, right? So those are, very interesting stuff to look at. And also you wonder, hey guys, why you focus on Logic framework? Why you look at TI framework, right? The screen on the right shows some statistics about the Bluetooth, low energy market. The market size. That is why. Remember in our seeking work, right? We call the firmware from Google Play Store, and you see 90% of them actually low-tech firmware, right? So there's some TI firmware there. So basically, this is also very consistent with other, market study. My point here is, right, find the interest domains, and as long as you can justify, right, the significance, and I'm sure you can, publish papers on those. And the takeaway of my talk is about, hey guys, it's so interesting, right? So cool, right? There are lots of potential for domain-aware analysis, and as security researchers, right, we always, guys, let's find vulnerabilities, right? Let's systematically vet those applications. I show you the numerous IoT applications, right? And the benefits of doing binary analysis, right, is we can, because binary is the final code that get executed, right? That is where our security researchers, right, can always look at this to find, flaws, vulnerabilities. This is also the difference, right, compared to like software engineering people. We are security people. What's the difference? We look at binary. Okay, they look at source code, right? So there are tons of opportunities, right, to systematically, look at, vet the flaws, right? You don't want that product has flaws, right, like used by other people. And you can extend, right, the findings in some particular domain to some other domains, right, or other frameworks, and do the binary analysis. You can, enable, right, downstream analysis. Like I talk about, hey guys, let's do control flow recovery. I'm sure once we enable the control flow recovery for the queued binaries, then fuzzing tool can be plugged in, right? Actually, my students work on the queued fuzzing. So because our tool resolves those control flow graphs, right? Now you can do the coverage easily, and so do dynamic analysis with that. So right, you can also generalize the methodology and insights to other similar domains. With that, I think that's all I have. Thank you.
How do you think the regular binary analysis tools work on these domain-specific applications, right? Because most of the analysis tools, they do kind of optimizations in recovery control flow graph, especially the one that you showed. Maybe, for instance, Anger might not recover the basic block after the if condition because it optimizes, it assumes that, hey, this read you're trying to read from zero that you have written, so the basic block is not reachable. So in the control flow graph that you get, you may not find that basic block. Similarly, in Qt binaries, if you use recursive disassembly, maybe some functions may not be recovered because there are no call instructions to that function. So how do you think binary analysis tool developers should work on when it comes to analyzing domain-specific binaries?
So maybe I have to think they're quite clear. So your question is how does the binary analysis tool work with domain-specific binaries?
Yes.
Right. So I always tell my students we do bottom-up research. So we play with examples, right, and find real-world problems, and then from there, right, we generate findings. So my point is, we cannot say top-down plan. My tool, this is an Anger tool, right? It's going to support this and that because we have no idea. It's plan, right? So instead, let's hands-on with play with the concrete, right, devices or framework code, all of those, right? Once you dig into the details, for example, like we did the work on this automap, right? So once we get there, we realize, well, the existing tools doesn't work. Then let's figure out why is that, and from those why questions, right? Why is that? Why this? Why that? And eventually can feedback to tools development, and the tools can domain knowledge, right, come from the bottom and then start to be generalized and then gradually start to integrate with various tools. But however, we talk about one size does not fit all, right? So if you look at the beginning of my talk, right, I talk about, hey, look at the evolution of computer industry, right? When I was PhD students, I look at x86, right? But today, when I still look at some other architectures, right? So it's evolving, and it becomes more fine-grained, right? So the dynamics becomes, this and that. So we cannot have a universal. I mean, some universal tools, right? Some fundamental tools, but it's, when the market has various, real applications, real devices, like for example the Qs, the Bluetooth, right? They're all different, right? You have to use domain knowledge to solve specific problems and which have, you should put processes in a lot. Yeah.
Thank you. Hi, Derek Key, MIT Legal Laboratory. There's a lot of possible domains one can analyze and become an expert, or gain some knowledge about that domain. Can you speak about ways in which we ought to be picking what domain would be best, as well as how deep of an understanding of the domain should you have in order to find effective methods for integrating that knowledge?
Wow, that's a good question. So, I cannot predict the future, right? I think if you look at backwards, so I also ask myself, right? I think security is interesting, and oftentimes we look at the ones that have deployed, right? We don't look at the ones that haven't been deployed yet, right? We look at the ones that's in market, and it's because security. Let's talk about malware too, right? We feel like define malwares, and then you can find malwares before software is deployed. That's why I would say software engineering people, right? So program analysis, right? The language is designed, whatever. First, you eliminate all the malwares as many as possible, right? And now the product goes to market, and now it's ours. We pick up, right? Say, hey, there's some test entertainment. Let's say how it works. Let's start to reverse engineer. Let's start to vet. Let's start to look at those, right? Sometimes, I don't know, I feel we have to say real products, especially the system security community, right? We don't say, and there are some research that's very, very, forward thinking, right? They are, some technology, far ahead, right? But if you look at what we, like I said, look at it, something like this once it's deployed, right? So if you say, hey, if I'm here, what are the products? AI assistants, right? Let's look at the AI assistants and what has to run in those AI assistants, right? Those domains. Yeah.
Thank you.
Hi, Andrea Continella, University of Twente. Thanks for the nice talk. So I was thinking, right? So nowadays, also with your talk, we see how we often find the vulnerabilities in these IoT devices, right? And I guess everybody know how the current state is very bad in terms of security for IoT devices. So my question is, so I think as a community we are kind of getting stuck into finding more and more vulnerabilities in IoT devices without actually solving the problem, right? So my question for you would be, what do you think we could do and how binary analysis can help in actually solving the actual problem, so either preventing or mitigating vulnerabilities?
Awesome, yeah. So if all the vulnerabilities are eliminated, so binary analysis people have what we could do, right? So definitely we should first be more proactive, right? Like during the software development phase, let's say you use memory stick languages like Rust, right? Now fundamentally the memory corruption types of vulnerabilities will be, the chances will be very low, right? But on the other hand, And you go before error, right? Because security is a forever problem. So always have anniversaries, right? Here we look at, vulnerabilities is one story in security, right? Of course, for software people like myself, right? We always either look at, do the malware analysis or vulnerability analysis because we look at binary, right? But I strongly believe there's a need for binary analysis because transparency. Look at the Volkswagen in that case, right? People have to study that. People have to vet those, right? I'm sure we all have secure jobs. I mean, binary analysis people have always, right? We have sensitive analysis. 100 years later, we still can analyze some AI binaries or something. Yeah.
Maybe a follow-on question. My name is Keynote, European Space Agency. 7 years ago at CCS 2016, there was a workshop on software transformation, which turned out to be another word for binary rewriting. The notion was to remove either excess unneeded code or to actually patch and maintain software that was abandoned by the vendor. And so I thought about this when sometimes people say this is the internet of unpatchable things. And I expect that some of the tools overlap. Has this actually been happening? Is there now a field where people routinely try to improve software by binary rewriting? Do you have a view on this?
Great. Actually, I said many people are actually working in that program, right? Debugging program, transform the binaries, right? So even myself was in that program. Right. When we do binary analysis, we analyze what is one, right? There are applications like patching, right? Rewriting, right? This is also actually the problem I have been working on for many years. Definitely, the binary, binary analysis in general. Fundamentally, like we cover consumer graph, we cover code, simple code, all those are fundamental problems, and the tools you develop there can be very helpful for downstream applications like patching,